So we have discussed about the Laplace transform, that is you can see in the previous module, that is we have the differential equation, then we convert that, we do the Laplace transform in S domain. After that we get the algebraic equations, then we find the solution of that, and after that we find the inverse Laplace transform, and finally we get the solution. So this you will see solution and the differential equation, it was in t domain, that is time domain, and this was in S domain, that is frequency domain. Now you will see that this Laplace transform is the method of solving the ordinary differential equations and initial value problems. Ordinary differential equations and initial value problems. The crucial idea is that the operations of calculus on the functions are replaced by operations of algebra on the transforms. That is, we can say that the differentiation of Ft will correspond to the multiplication of Laplace transform, and integration of Ft will corresponds to the division of LFT. So we have encountered such an idea in the logarithmic systems. Like in logarithm, what we do, that is the product of the numbers becomes the sum of their logarithms. So, and the division of the numbers becomes the difference of the logarithms. So that's the simple reason why the logarithms were invented in the pre-computer time. So it is important thing related to the Laplace transform, that it can be, these calculations, the solution can be found easily as compared to the differential equations. Now we will come to one simple problem, that we can discuss an electrical problem, that how we find some value at the time t, and then we can solve for the Laplace transform, try to solve for the Laplace transform and try to find the solution of that problem. After that you will have a great idea that how the things work in case of the Laplace transform. Now let us suppose a DC voltage is applied to the, let us suppose that DC voltage, the value of the DC voltage is 3 volt, and it is applied to RC circuit with the value of the R equals to 2000 ohm and the value of the C equals to 0.001 farad, and in this case the charge initially, the capacitor is uncharged, that is Q naught equal to 0. So that's the statement. So we have to find the voltage across the capacitor at the function as a function of t, that is we have to find the voltage equation as a function of t. So now the equation can be formed as, that is in this case one is R and second is capacitor C. So we can write R is 2000 into I can be written as dq by dt, Q is charge in this case, plus Q by C equals to V. So 0.001. It means that it is R into I equals to V across the resistor, and it is Q divided by C equal to voltage across the capacitor, and the total voltage is 3 volt. Now we get dq by dt. We get the equation as dq by dt plus 0.5 Q equals to 0.0015. Okay. Now we take the Laplace transform on both the side of this equation. Now we take the Laplace transform. From this Laplace transform, the equation would be, in case of differentiation, you will get S Qs minus Q naught, which is equal to 0 in this case, plus 0.5 Qs in S domain, which is equal to 0.0015 divided by S. So we have used the derivative property in this case, and in this case you will see that Q naught is equals to 0. Finally, we get the value of the Q as 0.0015 divided by S into S plus 0.5. So we can see that in the denominator, the terms, these are distinct roots are there, so we can use the partial fraction expansion, and I am not going in detail to find out the partial fraction expansion that has already been explained, and you have all also done in mathematics. So I will write simply the value of what the value of the coefficients coming out to be. So in this case we will see that Q equals to 0.003 divided by S minus 0.003 divided by S plus 0.5. So now we have to find the inverse Laplace transform in that very case. So we rub this equation, and since we have to find the inverse Laplace transform, and the inverse Laplace transform found out to be in this case is Q, small q, that is in time domain, Qt equals to 0.003 minus 0.0033 e raised to power minus 0.5 t. From the table 2.1 we can find the value of the Q in this case. Now we know that V equals to Q by C. So to find the voltage of the V, the voltage of across the capacitor is given by, which is equal to Qt divided by C, which is in this case is 0.003 minus 0.003 e raised to power minus 0.5 t divided by 0. The value of the capacitor in this case is 0.001. Finally we are getting the value of the Vt as 3 into 1 minus e minus 0.5 t. So in this way we get the final equation, that is voltage across the capacitor, as a function of time t. So this is one of the application that I have explained to you. After this lecture we can go for this transfer function, and then we can proceed further. Thank you very much.